know you're ready.
All right. Good afternoon. My name is Joseph King, and this is my senior capstone project for ocean engineering, and it is on providing machine vision to a competition AUV. So, autonomous underwater vehicles, or AUVs, rely on machine vision for navigation and autonomous decision making. And machine vision essentially allows the computer to see what is in front of it. So object detection, which is a machine vision task, enables the identification and classification of targets. So some of the applications of this include marine environmental monitoring. So AUVs, like in the picture here, can be used to detect different species of fish or marine life, and actually for population studies, biodiversity. There's also pipeline and offshore structure inspection. So you can have machine vision on the AUV to detect leaks in the pipelines or corrosion on the offshore structures. And there's also defense and surveillance operations. So AUVs, like the one shown here, can be used for a lot of different applications in the defense industry. One application would be detecting mines and actually identifying where those are at. Specific application that I was looking at was the RoboSub competition. So this is an international competition that's focused on AUVs, and student teams design AUVs to complete complex tasks in a controlled pool environment. And these tasks require detection and interaction with specific visual targets. So I was looking at the tasks from the 2025 RoboSub competition. Some of these tasks, the first one would be to navigate through a gate, and there's a shark, as you can see, on one gate and a sawfish on the other. And so whichever gate the AUV actually navigates through, it later needs to interact with the other task based on that, the gate that it went through. So if it went through the shark gate, it would need to drop items on one side of a shark or a bin that has a shark picture on it, or shoot torpedoes through a target with the shark in front of it. And you can see some of the examples here of different AUVs that RoboSub teams have used. So the 2025 competition had these tasks. They kind of vary year to year, but all of the competitions require object detection as a main factor in successful performance. So a little bit about the technical approach, the training and testing setup. So I developed a custom rig for controlled image collection, and I used a camera on this 3D printed camera mount to look through an aquarium at the different targets. And this kind of simulated, to some extent, some of the effects of underwater image collection with distortion and scattering effects. And I used a extendable painter's pole to be able to control the distance variation from the target, as well as a lazy Susan bearing on these two wood plates to be able to rotate left and right for different angles. And I used a protractor pointer system to monitor that angle variation and bubble levels on the camera mount to ensure that I was getting level image capture. So the first step in building the object detection models is image collection. So I collected images at distances of 30 to 65 inches from the target with 5-inch increments, and angles from 60 to 120 degrees if 90 degrees is head-on with the target, so 30 degrees in either direction. And 200 images were taken per target with 4 targets, so 800 total images. And then these images were trained by drawing bounding boxes, as you can see in these pictures, around the target, and then labeling them according to which target it was, so shark or the sawfish. And then the actual resolution of these models can be changed, or of these training images can be changed within an AI platform called Edge Impulse, where I built the models. So I'll talk a little bit more about that now, but the resolutions varied from 32 to 320 to see how resolution affected the performance of the models. So the first step within Edge Impulse to build the model is the data acquisition, so uploading all the images that you took and then drawing the bounding boxes and the labeling them. So you have to do that for all the images that you take, so that's a pretty lengthy process. After that, you can select the resolution you want to resize those images to. You select your image block and your model block. So you can do, I did object detection, you can do a variety of different models within Edge Impulse. The next step would be the image tab. So you actually generate the features that your AI is going to be learning from those targets. And you can see a feature explorer here that indicates how well those features are being detected for each target. So features can be contours, edges, colors, things like that. And this tight grouping with each target that are spread out between the targets indicates that it's distinguishing between those pretty well. Whereas if they were overlapped and the colors were mixed, it indicates that it's getting confused between those target features. Next, you actually select the settings that you want to build your model, and you choose the object detection model that you want to run. So you can see FOMO is selected here. That's faster objects, more objects. I use both FOMO and YOLO models, which I'll talk about in a second. And then you have a confusion matrix that's outputted at the end of this, which tells you, again, which features, which different targets are being confused with other targets. You can see an 18.9% confusion between the sawfish and the background here, for instance. So it's getting confused with some of those features. And then you can select the target device, so the ESP32, for instance, and it will actually output on-device performance estimates. So one of these would be inferencing speed, which tells you how long that model is taking to actually run one inference through the model, which is detecting one, or going through one detection of a target. So that's that tab. Then you go to live classification. You can view each of the images that you trained and what the object detection model is actually seeing for those there, as well as the model testing tab. So out of your 800 images that were uploaded, 80% were split into the training images and 20% were reserved for testing. So the model actually tests itself on these 20% of the images, and then you get an accuracy score of how well that model performed in detecting the right target. And then finally, you have your deployment tab. So you select your target type of deployment. So an Arduino library, for instance, you can have C++, Python, Linux, anything like that. Your inference engine you want to use, and your model optimization. So for me, the deployment, I did two different models, like I mentioned, FOMO and YOLO, to compare the performances between those two models. And I ran them on 3 different devices: a low-cost ESP32 CAM, a sort of mid-range cost Raspberry Pi 5, and a Jetson Orin Nano as the higher cost option. And I used Arduino IDE to flash the object detection models to the ESP32, and then ran the object detection models for the Raspberry Pi 5 and Jetson Orin Nano within the Edge Impulse Linux command line interface. And so these are a couple of videos to show you what the outputs for each model looks like. You can see FOMO here outputs centroids, so where it thinks the center of that target is. You can see the label here, as well as the confidence score, so how confident it is it's detecting the right target. Whereas YOLO outputs bounding boxes, so it actually draws the region of the target it's in. And the YOLO model, one thing I observed that was interesting was that it actually performed better with partial obstruction of the view of that target compared to FOMO models, which would completely lose all accuracy when any part of the image was obstructed. And that could be useful for the RoboSub competition, where you might have several targets or different objects that are overlapping with each other, so ensuring good performance there. Additionally, so as well as the kind of like live view outputs you can get these text-based outputs. So this is within the Arduino IDE serial monitor. You can see the object detection model. It's saying that it's detecting the Shark 2 target with a 99% confidence rating, and it's outputting the location that it's seeing that bounding box for the target, as well as the inferencing speed that I mentioned earlier, so 192 milliseconds. And then that code was adjusted to take 100 of those inferences and set a confidence threshold of what you want it to have for each target, as well as what target you want to be detecting there. And so it's going to tell you, okay, you have 27% of those 100 inferences are actually detections of the correct target with an above 80% confidence level. You have your blank frames and your wrong detections as well if you want a more detailed look into things. And so that was kind of my physical method for testing, but before I looked at those results, I did edge impulse, the estimated results with the on-device performance estimates. And so I did that for both accuracy and inference time for FOMO and YOLO models on the resolutions from 32 to 320. And you can see for inference time, the general trend is that with increasing resolution, the inference times are increasing for each device. The ESP32 with increasing resolution quickly got to like crazy inference times. So for FOMO models, up to 10 seconds for 320 resolution, and YOLO up to close to 100 seconds for 320 resolution, which is really just impractical times for the competition setting. You need to be able to accomplish tasks in a timely manner. The time limit is 15 minutes for the RoboSub run, so if you're standing there for a minute trying to detect one target, you're going to be in trouble overall. And then the Raspberry Pi was sort of in the mid-range there, but the Jetson was the fastest in the estimated results. And for accuracy, all of the models were above 95% accurate besides YOLO at really low resolution. So then I progressed to physical testing of these results. This was done on each of the devices, but there were several limitations with physical testing. The ESP32 was limited due to the high inference times at the higher resolutions. The tests were varying at different distances and angles with 100 inferences for each one, so quickly the time added up on these tests. So I was only able to test up to 128 resolution for the ESP32, and it was unable to run YOLO models, as well as not being able to run models bigger than the 256 resolution here for inference time. And the Jetson was limited due to a versioning issue with edge impulse that didn't enable me to use the command line interface for accuracy testing, but I was able to use a Python SDK method for the inference times test for it. So you can see that for the FOMO inference time versus resolution, ESP32, again, really high inference times, up to 10 seconds. The Raspberry Pi actually had lower inference time than the Jetson, which was unexpected for both FOMO and YOLO models. The Jetson's a NVIDIA product with, they specialize in AI computing, so you would expect the Jetson would have the higher performance there. And that could be due to the different deployment methods with the Python SDK and the Edge Impulse Linux command line interface. And then for accuracy, the ESP32 only got up to 40% accuracy at the 64 resolution, which is the best. So really low accuracy results there, while the Raspberry Pi FOMO model got up to around 95% accuracy with the 96 resolution, and around 92% accurate with the 224 resolution. And for the YOLO model, it kind of increased in accuracy with increasing resolution. And likely the biggest contributor to this device accuracy is the cameras that they're using. So the ESP32 is actually a really small camera you can see on this board, very low quality, very low resolution, whereas the Raspberry Pi was used with a higher resolution webcam, so that's probably a big contributor there. So this is more of the physical testing results. So this is kind of what the testing tables would look like for me, and these are averaged from all of the resolution models for FOMO and YOLO. And this shows just the positional accuracy variance for each one. So again, 90% being head-on with the target with 30-degree rotation in either direction from 35 to 65 inches. You see that the FOMO models aren't really affected very much by the positional variation, where the YOLO model actually shows a steady trend of decreasing accuracy with increasing distance from the target. And so to save time, those original accuracy tests were all done on one target, just the Sawfish 2 target. But once I identified the two most accurate models, so FOMO at 96 resolution and YOLO at 224 resolution, I tested those on all 4 targets. And the YOLO model actually had 15% higher accuracy than FOMO in that case. And you also see this trend where within 45 inches, there's 99% accuracy for that YOLO model, compared to the FOMO, where it's just a very random, seemingly variation of the accuracy with the positional variance. So this indicates that the YOLO model might be more consistent and reliable in detecting the target, especially if you can get to closer distances in the competition. Some of the main outcomes of the the competition. So edge impulse on-device performance estimations were shown to be relatively accurate for the inference times, but unreliable for accuracy. The ESP32 was shown to be insufficient for the overall machine vision for RoboSub competition, but it could be potentially used for the torpedo task because of its use of centroids. You can see the red boxes here, which match closely with the centroid output. Maybe a way to use YOLO to detect the general target and then actually switch to the FOMO model to shoot the torpedo precisely through the target. The Raspberry Pi was identified as a potentially viable machine vision solution for RoboSub due to its low inference times and high accuracy on certain model configurations. The Jetson needs further testing because of the versioning issue with edge impulse to determine the accuracy on it. FOMO models displayed the inconsistent positional accuracy variance, while the YOLO models had a steady trend of high accuracy close to the target, where it was low accuracy farther away from the target. The budget used for this project, the Raspberry Pi 5 and its accessories were $200. The NVIDIA Jetson Orin Nano and accessories were $288. The cameras used in this project were $167, including 2 stereo vision cameras, which I'll talk about on the next slide. The testing setup was $108 for a total of $764, and the funding for this project came from an Eagle Spur grant. So methods, reflection, and analysis. I spent too much time trying to get object detection models running on a stereo vision camera. And you can see an example of a stereo vision camera here. It allows the computer to be able to tell how far targets are away from it. And I tried to get the object detection models from Edge Impulse running on these cameras, but the expected resolution from Edge Impulse was way different than the input resolution of the cameras, which caused a lot of problems. And in reflection, I could have tried to get the stereo vision working on these cameras while just running the object identification on other cameras and used the 2 of those in combination. The wood boards used on my testing setup actually warped really quickly in like a week, so they completely bent. It could be from just the pressure of the screws pulling with the bearings and the lazy Susan bearing between them. But I could have used plastic or some other material that wouldn't have warped as quickly. And then the Jetson CSI ports are really easy to break. You can see them down here. For use with the stereo vision cameras. And the little insert pin here that you have, the sides of it with a clip can break really easily, and then you can't use that CSI port anymore. So skills and lessons learned. I got familiar with using Edge Impulse, Linux, Arduino IDE, robot operating system, which I'll talk about on the next slide, Python, Raspberry Pi, NVIDIA Jetson Orin Nano, and then data analysis in Excel for the different tables and plots. Soft skills, I had improved time management, project planning, troubleshooting, and communication of technical concepts. And an unexpected realization was that the object detection model accuracy is highly sensitive to the training conditions, the resolution, model type, target position, and camera orientation. So small changes can have a huge effect on those models. So the future work and research. Resolving the versioning issues and evaluating the accuracy performance on the Jetson Orin Nano, comparing the performances with different cameras on the same device, so a USB webcam and RGCam, for instance, on the Raspberry Pi, to be able to determine how much effect the actual cameras have on accuracy. And then designing or purchasing an underwater housing for accuracy testing in a pool setting. Here's some Blue Robotics housings that could be a good option for the RoboSub team. Developing the stereo vision capabilities. So I did a lot of work trying to get that to work, including setting up a robot operating system node architecture. Robot operating system is likely what the RoboSub team will be using, and essentially allows you to have different nodes, which are sections of code to control certain parts of the AUV. So you might have a thruster node and a camera node and a gyroscope positional node. So I did a lot of work on the stereo vision for that, and had an image capture node and then split into left and right images for each camera, as well as an object detection node containing the edge impulse model and a detection overlay node to output the overall output from that system. All of that was working together correctly, but the object detection node wasn't correctly pulling the detections from edge impulse, so that issue still needs to be resolved. And then synthetic imaging supplemented into the object detection models. So synthetic imaging allows you to recreate the competition settings, so lighting conditions, the background of the pool, all of that stuff before the competition happens. A lot of times teams train with, in a different pool setting, they take their training images, and the lighting conditions and all in the competition are different than the real ones, and that can affect the model accuracy significantly. So synthetic imaging allows you to actually prepare that model beforehand and have sort of a base built up, and then the day of the competition, the teams can supplement with those physical training images. And that's it. Questions?
So your test showed that you put your target in like an aquarium, stuff like that, right?
Or, yeah.
If you go into a pool, my concern is that how much of light on the ceiling is going to introduce noises, because there's going to be a little bit of like noise and things like that, and that is might introduce some inaccuracies into your model.
Yeah, so the models are really sensitive to the lighting conditions and all of that stuff, like I was saying. So this was mainly to evaluate the different performances of the models, but for actual competition performance, you need to do the training in that pool, or like I said, have synthetic imaging that very closely models what the pool setting will be like, because those factors do influence the accuracy a lot.
The other question I have is that have you considered using like something fast YOLO and then mix it with something way more accurate like a CNN?
Potentially, yeah. These were the two models that I analyzed. I did look at other ones, but these were the main two that were within Edge Impulse. Several teams actually sort of build custom models, which actually play on 7 or 8 different types of object detection models and sort of work all together. They have different weights associated with each one according to the distances and all. So future work can look into that for sure.
The last question is that your Raspberry Pi works better than Jetson, but which one uses less power? That's right.
I believe that the power draw was similar for both of those, but I'm not sure.
Because sometimes you see a very small CPU does the job, but just
Right.
runs so hard.
They have the exact same CPU metrics. The difference between the two is that the Jetson's GPU is way stronger than the Raspberry Pi, which allows it to handle a lot of that AI stuff better. So it was really surprising that the inference time was lower on the Jetson, or on the Raspberry Pi.
Very good, Jeff.
Yeah.
So from my understanding, you explored very fixed camera positions at different distances. 2 questions. How would like moving camera movement due to like, maybe, I'm not saying that's going to be currents in the pool obviously,
Yeah.
but the unsteadiness of holding a fixed position, have you ever explored?
Yeah, so there's actually, I did do some of the research. I couldn't put it in the presentation, I didn't have time, but on the actual roll of the camera, so just adjusting that mount left and right, and I actually found that slightly shifting that, I mean like 5 degrees or so, can make it drop from 99% to 0% accuracy, so it can have a huge effect on it. So that'll be a big part of the AUV. One, getting a model that's less versatile with all that, less volatile, but also making sure your gyroscopic system is keeping that AUV as stable as possible.
Could you add to the data as training images, just having those images at 360 degrees so it could recognize it in any case?
Yeah, the more versatile your training image base, the better that model's generally going to perform. The main factor there is just the amount of time it takes. So you got 800 images you got to train manually. It's going to take several hours. So that's where some of the synthetic imaging comes in, where you can do that automatically with different distances and angles and all of that stuff.
Kind of related, I think you looked into image augmentation.
Yeah, so Edge Impulse actually already does or has a setting for image augmentation. So it's where essentially the color, the different slight angle adjustments, different slight changes like that of the image quality are actually changed, or augmented by the system. And so that's something that Edge Impulse does, but you certainly can do that on a larger scale for similar reasons to what they're saying.
Also, when you showed your accuracy down to 50%, is this just a two-object model? So 50% pretty much implies no skill at all? Like a 50-50 chance? Or is it, you see what I'm saying? When you had your matrices, where you showed it goes down to 50% inference accuracy.
Right.
If you have only two models and you get 50% accuracy, that pretty much means a random shot, right? No skill at all. Is that correct? That's how I need to interpret that?
The threshold used was 80% confidence. So if you were to lower that threshold, then potentially your accuracy would go up from 50% to 75% or 80%. So it could depend on what your expectation is on the confidence threshold that it needs to be at.
Okay, so 50% means in 50% of the cases you had 80% accuracy. Is that how I need to interpret that now?
The confidence threshold is just how confident that model is, or the AI is, that it's detecting.
So go to your slide where you show the tables.
Okay.
Yeah, right there.
Mm-hmm.
So if you have 55% accuracy,
Right.
does this mean 55% of my images are classified the right way? Or?
Yes.
Right. So if it would be 50% and I have a two object model, then it's pretty much just luck, right? So it implies no skill, I would imagine.
Yeah, I mean, it's 50-50 shot.
Yeah.
I have a follow-up question. So, how would you adjust that confidence level in the competition? So, like you just mentioned, would you prefer to reduce it if it's a time competition and you want to do things fast and move on to the next task? Or would you rather increase the confidence level if you get more points for completing tasks successfully?
Definitely depends on your priorities for the competition. If you lower that confidence threshold and then you incorrectly detect a target and make the wrong decision, obviously you're going to get no points for that task. You did the wrong thing. But you can get a lot of points for making a faster run through the competition. So it's just a give and take balance, and some of that might come from competition experience after a few years of the competition, learning what works and what doesn't, and what thresholds to use for that.
Probably want to have a pretty good threshold for the gate selection, so we don't.
Yeah. Do all the rest of the tasks wrong. Yeah, that would be not good.
Anybody else? All right. Very good.